today's lecture, we will start with the basic properties of the integrals we defined before, which is proposition 1.7, which gives us the idea that if f and g are two continuous functions on closed interval ab and gamma and sigma are functions of bounded variation on closed interval ab, then for any scalars alpha and beta, integral from a to b alpha f plus beta g d gamma is equal to alpha into integral a to b f into d gamma plus beta into integral a to b g into d gamma. And the next property is integral from a to b f d of alpha gamma plus beta gamma beta sigma is equal to alpha into integral from a to b f d gamma plus beta into integral from a to b f d sigma. You can prove this result very simply by using the usual epsilon delta argument and how we proved the earlier theorems. And also another interesting proposition is 1.8, which gives a generalized version of what we just said before. That is, if gamma is a bounded variation from closed interval ab to c, and f is a continuous function from closed interval ab to c, and if our interval is divided into subintervals partitioned, then integral from a to b f d gamma is equal to summation k is equal to 1 to n integral from tk minus 1 to tk f d gamma. So this means that if we introduce a partition for the subinterval, we can sum up the integrals of each portions to get the whole integral from a to b. So you can try out this proposition also along with proposition 1.7 to prove it as an exercise. Now let's move on to theorem 1.9. Theorem 1.9 says that if gamma is a piecewise smooth function and f from closed interval ab to c is continuous, then integral from a to b f d gamma is equal to integral from a to b f of t gamma dash of t dt. You might be familiar with how we integrate in complex analysis in your degree course, and this is the same definition of how we integrate here too. So we'll see how this theorem can be proved. So here we are considering definitely our gamma is a curve inside our complex plane. So we are considering this gamma as like this. For example, gamma is equal to gamma real part plus I into gamma imaginary part. This is I'll call it real and I'll call this imaginary. So this is how a particular point in gamma, the curve is like, right? For every point, we can write gamma like this. So for making our proof go in an easy manner, we are considering that this gamma is actually happening like this. Gamma of closed interval AB is lying completely inside R. Right, that means I am just leaving out this. I am saying that this gamma is only taking values from R. Okay, so that is one consideration. And also we consider that gamma is smooth. In our statement, it says that gamma is piecewise smooth, and we are saying that gamma is smooth because that will also enhance our easiness because we can think about portions of the subintervals from the earlier theorem which we just mentioned now. Okay, so we are considering gamma is smooth, and also we are looking at the real and imaginary parts of gamma, and we are reducing it to gamma of closed interval AB is coming inside the real axis. That means the values of gamma are lying inside the real number line. Okay, that is our basic assumption now here. Now let epsilon be greater than 0, and we are choosing a delta strictly greater than 0 such that we are partitioning our closed interval AB, which is P. The partition is called P, and the partitioning is like A is equal to T naught strictly less than T1 strictly less than T2 strictly less than etc. strictly less than Tn, which is equal to B. And also we are saying that this norm of P, which is the maximum length of all the subintervals of closed interval AB, that is strictly less than delta. Okay, we are assuming all these things. And if this is happening like that, by the earlier theorem which we proved, we know that modulus of integral from a to b f d gamma minus summation k is equal to 1 to n f of tau k into gamma of tk minus gamma of tk minus 1 is strictly less than 1 by 2 epsilon. Why did this happen? Because we are using theorem 1.4 here, and here we know that this gamma is smooth. It's piecewise smooth, and we took it to be smooth. And if gamma is smooth, we already proved that gamma will be a bounded variation. Okay. And also we say that f is continuous. Okay. And that is the basic hypothesis of theorem 1.4. So everything is satisfied. So we can say that there exists a complex number I such that whenever epsilon is greater than 0, there exists a delta greater than 0, such that if we partition the closed interval AB such that its norm is strictly less than delta, then we can say that this inequality is true. That is what theorem 1.4 says. So we have this inequality, and also consider modulus of integral from a to b f of t gamma dash of t dt. Okay, you're considering this, and that can be made very close to summation k is equal to 1 to n. Here you have f of t, so here you have f of tau k, here you have gamma dash of t, here you have gamma dash of tau k, okay, into here we have dt, so we have a difference tk minus 1. So the modulus of that is also strictly less than epsilon by 2. We can make it like that. So these are two basic observations we get, inferences we get when we assume all these things. So this toke, which is coming here and here, okay, this toke is any number which happens to be inside the subinterval tk minus 1 tk closed interval. Okay. Now we are going to apply mean value theorem for derivatives. Mean value theorem for derivatives says that suppose if f of x is a continuous function, it is continuous at every point of the closed interval AB, and it's differentiable at every point of its interior, then there is at least one point C in open interval AB at which f dash of C is equal to f of B minus f of A divided by B minus A. This is our mean value theorem for derivatives. So we are going to apply this for gamma. This, this gamma is a smooth function from closed interval AB to R, right? Because we assume that the values of gamma is coming only from R. So you can make it like this. And also it is piecewise smooth. That means definitely inside the closed interval tk minus 1 tk, gamma will be smooth. It will be, yeah, it's piecewise smooth, so in this subinterval it will be smooth. So gamma can be considered as a function from closed interval to tk minus 1 comma tk to r, and it is continuous. Obviously gamma dash is also continuous because it is smooth, right? So we can apply this mean value theorem and say that there exists a tau k inside this open interval tk minus 1 comma tk such that Gamma dash of tau k is equal to gamma of tk minus gamma of tk minus 1 divided by tk minus 1. So that's what we have it here. Gamma dash of tau k is equal to gamma of tk minus gamma of tk minus 1, the whole divided by tk minus 1. So that's how we apply the mean value theorem. Now consider this summation. The first summation we had from theorem 1.4, which came like this in the inequality. So that is summation k is equal to 1 to n f of tau k into gamma of tk minus gamma of tk minus 1. I'm calling it s. Say I'm calling it s. Okay, that is equal to, so instead of this gamma of tk minus gamma of tk minus 1, I can say that is equal to gamma dash of tau k into tk minus one. So I'm substituting what I got from the mean value theorem. Okay. Now consider modulus of integral from a to b f d gamma minus integral from a to b f of t gamma dash of t dt. Okay. That is equal to modulus of, I'm going to say, integral from a to b f d gamma minus s plus s. No offense, minus this, right? So apply the triangle inequality on modulus so that you get this is strictly less than modulus of integral from a to b f d gamma minus s plus modulus of s minus integral from a to b f of t gamma dash of t dt, right? So s is nothing but this, and also s is nothing but this. So you have the first term inside the modulus to be strictly less than epsilon by 2, and also the second term inside the modulus here also less than, strictly less than epsilon by 2. So you get both of the term is strictly less than epsilon by 2 plus epsilon by 2, that is equal to epsilon. And since this epsilon is a positive number and it is arbitrary, you can say that this summation integral from a to b f d gamma is equal to integral from a to b f of t gamma dash of t dt. So that is a very important step we make after we defined this integral. And we know that a path is a continuous function from closed interval AB to C. So if gamma from closed interval AB to C is a path, then we say that gamma of t from A to B when t is varying, okay, that is called the trace of gamma. That means the points this gamma takes inside C is called the trace of gamma and is usually denoted by set gamma, and it is a compact set. And also we say that gamma is a rectifiable path if gamma is a function of bounded variation. Okay. And if P is a partition of closed interval AB, then V of, what was V? V was the, yes, we said we denoted it with the bounded variation summation, right? So this v of gamma p is exactly the sum of lengths of line segments connecting the points on the trace of gamma. Also, to say that gamma is rectifiable, gamma has finite length and its length is equal to capital V of gamma, which is nothing but the total variation of gamma. And also, if gamma is piecewise smooth, then gamma is rectifiable and its length is nothing but integral from a to b modulus of gamma dash of t dt. So this is an important set of definitions coming here. These are, and also if gamma is a rectifiable path with the trace contained in E contained in C, and if f is a continuous function from this E to C, then f composition gamma is continuous on closed interval AB. You can just work all these out, which are very easy to make sense. Okay. And the next definition is nothing but how to define the line integral. If gamma is a rectifiable path, you know what is a rectifiable path from the earlier definitions? That means gamma is of bounded variation. And f is a function defined and continuous on the trace of gamma, right? Then the line integral of f along gamma is nothing but integral from a to b f of gamma of t d gamma t. That means f composition gamma of t d gamma of t. So this is usually denoted by integral over gamma f or integral over gamma f of z dz. Okay, and for an example there of the line integral, suppose if gamma is the rectifiable path from closed interval 0 to 2 pi c, which is nothing but gamma of t is equal to e raised to it. You know that that is forming a circle with radius 1, right? Unit circle. Define f to be equal to 1 by z. Okay, that is continuous on this, definitely on the points of gamma, right? Because and this f is, we are taking z not equal to 0. Okay. Now gamma is differentiable by the theorem which we mentioned earlier, theorem 1.9. So we can calculate integral over gamma 1 by z dz will be equal to integral from 0 to 2 pi e raised to minus it into I into e raised to it dt. That is equal to 2 pi. That's how we used theorem 1.9 there. So there are some basic analysis you can do in the next paragraph too. And let's move on to preposition 1.13, which says that if gamma is a rectifiable path from closed interval AB to C, and C is a function from closed interval CD to closed interval AB, it is continuous and non-decreasing function such that phi of C is equal to A, phi of D is equal to B. Then for any function f continuous on the trace, integral over gamma f is equal to integral over gamma composition CF. To prove it, suppose epsilon is strictly greater than 0, we have to choose delta 1 strictly greater than 0 such that we are partitioning it S naught strictly less than S1, strictly less than etc., strictly less than Sn, and a partition of closed interval CD with modulus of sk minus 1 is strictly less than delta 1, and also sigma k is coming inside sk minus 1 and sk. Then by the earlier theorem, we get that modulus of integral from gamma composition cf minus this whole summation is strictly less than epsilon by 2. Similarly, working out the same on the partition in between T naught and Tn, and just exchanging delta 1 to delta 2, okay, and instead of this sigma k you have tau k, instead coming for this tk minus 1 and tk. The same theorem can be used here to get modulus of integral from gamma f minus this whole summation is strictly less than epsilon by 2. And also we know that this C is uniformly continuous on closed interval CD. Hence, there is a delta strictly greater than 0 which can be chosen such that delta is strictly less than delta 1, such that modulus of this C of S minus C of S dash is strictly less than delta 2 whenever modulus of S minus S dash is strictly less than delta. This happens because C is uniformly continuous. So if the partition S naught strictly less than S1, strictly less than etc. Sn is partitioning closed interval CD such that the modulus here is strictly less than delta, strictly less than delta 1, and this Tk is equal to C of Sk, then the partition T0, T1, etc. Tn is a partition of closed interval AB such that modulus of Tk minus 1 is strictly less than delta 2. And also if sigma k is here and tau k is equal to C of sigma k, then we can say that both of the inequalities sitting here in 1.14 and 1.15 will hold simultaneously. And that will make us obtain the fact that modulus of integral from gamma f minus integral over gamma composition C f is strictly less than epsilon. And since epsilon is arbitrary, equality is proved. You can prove it very easily by using the theorem which we mentioned earlier and using the correct partitions, correct usage of epsilon, delta 1, delta 2, also sigma k and tau k. And also that C, the function C is uniformly continuous. Using all these facts, you can easily make the preposition 1.13 to get proved. Okay, and we have some definitions here which says that if sigma and gamma are two rectifiable paths, the path sigma is equivalent to gamma if there exists a function c from closed interval CD to closed interval AB, which is continuous and strictly increasing, such that C of C is equal to A and C of D is equal to B, such that sigma is equal to gamma composition C. And such a function C is called change of parameter. A curve is nothing but the equivalence class of such paths. So let's wind up today's video lecture and do work out the theorems we mentioned and also the logical reasoning of preposition 1.7, 1.8 using the epsilon delta norms, okay, and also move through it very easily. So thank you.